Welcome back to our classroom. Here we are going to discuss about toroid. So generally what is called toroid means is slightly bend of solenoid. A solenoid is slightly bent, that we are saying that toroid. Okay. Then we directly go to the topic here. The magnetic field due to toroidal solenoid. So how it's initially look like in the sense. See, this is the interior, this is open space. This one is open space, and we have the first circle, second circle, third circle, fourth circle, right? It's clear? So here we have wounded with some connection with wires, okay? And here we are providing some current to that toroid solenoid, right? Now this is the typical diagram for toroid solenoid. Now we go for a cross-sectional view of toroid. So here we have the first circle, right? That I am going to take as the first ampering loop, okay, which is look like into the paper, into, right? All those things I mentioned as into. And the second one I have mentioned here, that is onto. I mean the dot I am kept here, right? And the third ampere loop I am taking here. So in that toroid I have chosen three different ampering loop. This one, and the outermost ring I have chosen as 3 ampering loop. What's our aim in that toroid in the sense? We are going to find out the magnetic field inside the toroid, that means open space, and exactly inside the toroid and outside the toroid we are going to calculate now the magnetic field. Right. First one, the open space interior to the toroid. What is the open space? Yes, of course, this point P. So here also we have point P, which is located inside this first ampering loop, right, which is in open space. As is very clearly from the picture, in that open space there is no current. If there is no current means obviously there is no magnetic field in that point, right? So here I have discussed L is equal to 2 pi r. That is, the circumference of the circle is 2 pi r and the current is 0. According to Ampere circuiting law, BL is equal to mu naught I, right? So here I is 0, therefore B is 0. And the second case, the points which is inside the toroid, this is the inside, right? So in the inside we are going to calculate, again the same rule we are going to use. We are going to use Ampere circuiting law, B into 2 pi r, which is equal to mu naught Ni. Why we need to use N here? Yes, of course, we have the number of turns in solenoid, right? So here I have include N, the number of turns. What is number of turns? N. This N is, that N is 2 pi r N, right? 2 pi r small n, right? So substitute over here, B is equal to mu naught Ni divided by 2 pi r, and N is equal to 2 pi r N, right? So substitute over here, this 2 pi r will be cancelled. We will have the magnetic field in terms of mu naught Ni. So here the magnetic field depends upon the turns and the current which is passing in that toroid. This is the inside the toroid. In the third case, open space outside the toroid, this place. Okay. For this one I am going to consider this third ampering loop. Look at the first ampering loop and second ampering loop. So what about the direction of these two ampering loop? Yes, this one goes in that clockwise and this one will goes in the anti-clockwise. Okay. So this, the third ampering loop, consists of two ampering loop, loop 1 and loop 2, right? So loop 1 is going in onto the paper, into the paper, right? And this one is out of the paper, right? So that ampering loop 2 is out of the paper, ampering loop 1 is into the paper. Therefore, it both cancel each other, and outside this toroid, the magnetic field value becomes 0, right? Here I wrote each turn of the toroid passes twice through the ampering loop 3, into and out to, okay, into the as well as out of the paper. They are cancelled to each other, therefore I becomes 0. Obviously the magnetic field becomes 0. I hope you understand well. Thank you. See you in the next video.